Hello everyone. This is topic 8 and topic 9 for exam 4. Topic 8 is alternating series. So as the name suggests, terms of the series would alternate. So here we wrote out the terms of this series. Just simply, I didn't show it explicitly, but the first term of course is negative 1/3 to the 0. Then we have negative 1/3 plus the negative 1/3 to the first, and then this one plus negative 1/3 squared, and so on. So I just took liberty to write them out. So we've got 1 minus 1/3 plus 1/9, etc. And it is a geometric series. Value of r is negative 1/3, so we can determine its convergence or divergence easily. What we want to do, though, is consider the fact that it's alternating signs, each of the terms. Consider rewriting this. Instead of, here's what I'll do. Instead of negative 1/3 to the nth, I'm going to write it as the product of negative 1 times 1/3 as a quantity to the nth. And then just use the basic rule for the power of a product, where we could take each factor and raise it to that power. So we'll write this as the sum as n goes from 0 to infinity of negative 1 to the nth times 1/3 to the nth. So the point being that this factor of negative 1 to the nth is what I like to call the alternating factor. So that's basically what's causing the terms of the series to alternate sign. So we have a theorem regarding convergence or divergence of this type of series that contains an alternating factor. First off, we say let a sub n be greater than 0, and that just is telling us that this portion is always going to be positive. The negative 1 to the nth, notice, is in the formulas here. Could either be negative 1 to the nth, negative 1 to the n plus 1th, depending on if you want the first term negative or positive, and the indices can change as well. But no matter what, if it has that factor, that alternating factor of negative 1 to some n power, then it's called an alternating series. And it's going to converge if the following two conditions are met. The limit as n goes to infinity of a sub n is 0, and a sub n plus 1 is less than or equal to a sub n for all n. Now, the idea of what that means is as follows. Consider a number line, and let's say we add up the first 1,000 terms of the series, and we get a sum, the 1,000th partial sum. And let's say that the term that we just added on was a positive term. And we're assuming that it's going to converge, so we're going to assume that these two conditions are true. The next term that we add on will be a negative term. And so maybe somewhere over here to the left would be the 1,001st partial sum. But if these two conditions are true, what this is saying is that the next term is smaller than or the same as the previous term. So a sub n plus 1, when we write out the terms of a series, a sub n here, a sub n plus 1 is the next term. So it's saying the next term is small, let's assume smaller than the previous term. Well, that would mean that if this was a negative number, negative term that we added on, the next term that we add on will be positive, but it's going to be smaller than this distance. So therefore, maybe somewhere over here to the 1,002nd partial sum. And at the same time, if that keeps on happening, the terms are getting smaller and smaller. And the terms are approaching zero, the limit, as we go further and further out, excuse me, of these terms are approaching zero, then basically what's going to happen is, okay, that term was positive that we just added on. This term's going to be negative, but it's going to be smaller. So here's the 1,003rd partial sum. And then it's just going to keep on kind of bouncing back and forth, but it's going to converge to a specific value. Okay? So that's the idea behind the convergence or divergence. The proof is certainly more complicated than that, but at least that gives us an intuitive sense as to why these two conditions will verify convergence of an alternating series. Now, all that you need to do is be able to show those two conditions. And on your table of the test for series, if we look toward the bottom, there's the alternating series. It has the form, which we stated, and it says, it puts it in the opposite order, though. Instead of having the limit, I like to look at the limit first, and you'll see why through example. But he has the limit second. If you want, put a little Roman numeral 1 next to the limit, and a little Roman numeral 2 next to the inequality. Because I like to look at the limit first. Now, it doesn't matter. Whatever you want to do, it's your choice. But I'm going to suggest that. Now, when we identify, and I'm going to be very explicit on the exams and tell you the type of test to use, so determine convergence or divergence of the alternating series. So you go to your table and you read it, because I'm not forcing you to memorize these theorems, and you read it and you say, okay, he said look at the limit first, so that's the first thing you consider. It is the limit as n goes to infinity of a sub n. So that would be the limit as n goes to infinity of 1 over n cubed. And then by inspection, you could say that's 0, because you have a constant in the numerator and the denominator is increasing without bound. Or if you wanted to throw infinity in there, infinity cubed certainly is infinity. In the limiting sense, dividing by infinity, if we have a constant in the numerator, it's 0. So I'll put a little check mark saying it passes the first condition for convergence of an alternating series. Second condition is to show that a sub, well, he uses a sub k. If you want to use, let's do that. Let's use a sub k plus 1 is less than or equal to a sub k for all values of k. So I used an n up here when I stated the theorem, but since you're going to be using your table most likely, maybe let's state it the way he did. Actually, he reversed the order even of the inequality, as you can see here. He's got a sub k is greater than or equal to a sub k plus 1. So let's actually be consistent with his method. And so we'll show that a sub k is greater than or equal to a sub k plus 1 for all values of k. Now, this might seem a little bit odd at the beginning, but it's really just like functional notation. If we have that a sub n is 1 over n cubed, if I wanted, like, let's say the fifth term of the series, like a sub 5, well, that would just be 1 over 5 cubed, because all I'm doing is replacing the n by 5. So just like functional notation, if I want a sub k, that's replacing the n by a k, so 1 over k cubed. And similarly, if I want a sub k plus 1, that's replacing the n by k plus 1, so 1 over, as a quantity, k plus 1 cubed. And then we can determine that the inequality is greater than, because the denominator on the left is always smaller than the denominator on the right, and so therefore its reciprocal will be greater than. Remember, we did this before with the direct comparison test. You want to just plug in a number, plug in like a 1. Here you get 1, here you get 1 over 2 cubed, or 1/8, and 1 is bigger than 1/8. But I'm going to argue it in general. But now that passes the second condition for convergence of an alternating series. So then we could say that by the alternating series test, the sum as n goes from 1 to infinity, this given alternating series that we have here, converges. Okay, so a second example. And we have, just to check those two conditions. So first one, the limit as n goes to infinity of a sub n has to be 0. That's the limit as n goes to infinity of 1 over n squared plus 1. And that will have to be 0. And by inspection, you could say it's 0 because you have the constant in the numerator and the denominator is increasing without bound. Or if you want to show a direct substitution, 1 over infinity squared plus 1, certainly 1 over infinity, and in a limiting sense 0, so it passes the first condition. And for the second condition, we have to show that a sub k is greater than or equal to a sub k plus 1 for all values of k. And again, the way to show that is just to show me that you understand what a sub k and a sub k plus 1 means. If a sub n is 1 over n squared plus 1, a sub k is 1 over k squared plus 1, because you're just replacing, you're just replacing the n in a sub n by k. And then a sub k plus 1 would mean 1 over n gets replaced by k plus 1. So 1 over k plus 1 squared plus 1. And then we could argue similarly that this denominator on the left always smaller than the denominator on the right, so therefore the reciprocal is greater than, and so that passes the second condition. So then once again, by the alternating series test, this series the given series, I always like to rewrite it, that this converges. Alright, so one last example of the alternating series. And this one will illustrate why I like to look at the limit first. So the first thing we do, it's an alternating series. We're told to determine its convergence or divergence. So you look at the table. If you doctored it up, it's suggesting look at the limit as n goes to infinity of a sub n first. And that's the limit as n goes to infinity of n cubed plus 1 over 5n cubed plus 1. But then immediately by inspection, because you have to recall our famous shortcut method for this type of limit, when n is approaching infinity and we have a ratio of two polynomials where the degrees are equal, the limit is just the ratio of the leading coefficients. And the coefficient of this n cubed is 1, and so therefore by inspection it's 1/5. The theorem said it had to be 0, so if it's not equal to 0, then immediately we could say that it diverges. So that's why I like to look at the limit first. Because if the limit's not 0, we're done. And there's no need to show that term by term comparison of a sub n or a sub k and a sub k plus 1. But I want to make sure you understand why it diverges. The reason why it diverges is not because this is really what we just did by doing this is really the nth term test. The first test we ever used was the nth term test, which says it diverges if the limit is not 0. And we argued that the fact is, if the limit is not 0, you're adding on some number, an infinite number of times, so obviously the sum of your series is going to increase without bound. But this is not increasing, the sum of this particular series is not increasing without bound because it's an alternating series. The reason why this one is diverging is because if you look at that number line concept that we talked about, and let's say you add up the first 1,000 terms of the series, and then the next term you add on, and let's say the last term you added on was positive. The next term you add on is going to be negative, and so it'll bring you somewhere over here to the 1,001st term of the series, so the 1,001st partial sum. But see, this distance is going to be, for this example, approximately 1/5. Because as we go way out there, in terms of the value of n and how far out we are in terms of how many terms of the series we wrote out, this series is approaching 1/5. So that distance is about 1/5. Well, then the next term that you add on is also going to be about 1/5, but it's going to be positive, so it's going to basically bring you back. So this one brought us to this sum, but then this is going to bring us back roughly to that sum for the 1,002nd partial sum. And then it just keeps going. This would be the 1,003rd partial sum and 1,004th here. So the reason why it diverges is because the limit, so it diverges because the limit of the partial sums does not exist. So you really don't have to worry about that mechanically. If you got a problem like this and you just brought it to this point where the wavy line is, I'm going to be satisfied. But that's just to show you the concept. All right, we'll start talking about absolute and conditional convergence. And it's kind of, as we're going to see, a strength, a level of strength for convergence. I mean, think of it absolutely or conditionally. You know, absolute is a stronger term rather than conditional based on some condition. So consider this series. So it's an alternating series. And let's say that we make all the terms positive. Okay, first off, well, let's do this. What does this series look like? Well, when n is 1, negative 1 to the second would be positive 1. 1 over 1 squared is 1. When n is 2, it would be a negative, because negative 1 cubed, 1/4. Next term positive, n is 3, 1/9. Next term negative, n is 4, 1/16, and so on. All right, now we're going to make all the terms positive. So here we've got an alternating series. We don't know if it converges or diverges, but we're going to make all the terms of this series positive. So basically what we're going to do is take the sum and goes from 1 to infinity of the absolute value of negative 1 to the n plus 1th times 1 over n squared. And if you wrote out the terms, they're just simply going to make everything positive. Okay? Now the question is, what happens with this series? Does this new series, by making them all positive, converge or diverge? Well, if you consider what the absolute value does, is it basically allows you to take away the alternating factor and drop the absolute values at the same time. Because this series, 1 over n squared, is the same as this. Because the absolute value just removed the alternating factor. Because if it's positive, a term's positive. If it's negative, the term is negative. And this is a p-series. And the value of p is 2. So hopefully you recognize that as a p-series, 1 over np. Value of p is 2. If you have to look at your table, when p is greater than 1 in a p-series, then it converges. So then the question would be, well, what about the original series? When you had negative terms. So the negative 1 to the n plus 1, 1 over n squared. Well, just intuitively, we would have to say that this converges. Because if we made all the terms positive, and we were able to show that the series converged, then it converges to some number. So then if we take away some of those values by making some of those terms negative again, then obviously the sum is going to be less than whatever this sum is. So intuitively we would say it converges, and that leads us to our definition for absolute convergence. If the sum of the absolute value converges, then the sum of the series also converges. But the converse of this is not true, because this is only an if-then statement. And consider this series. If you take the sum of the absolute value of this series, that becomes the sum as n goes from 1 to infinity of 1 over n. 1 over n is the p-series, but that's the famous p-series, which is the harmonic series, where p is equal to 1. And when p is less than or equal to 1, look at your table if you have to, once again, regarding convergence or divergence of the p-series, right? It diverges if p is less than or equal to 1. So therefore it diverges. But by the alternating series test, we have that the first thing to consider was the limit as n goes to infinity of a sub n. There would be the limit as n goes to infinity of 1 over n, which is 1 over infinity or 0, so it passes the first condition. And then we want to show that a sub k is greater than or equal to a sub k plus 1 for all k. And a sub k is 1 over k. A sub k, 1 over k plus 1, because we're just replacing the n by k and the n by k plus 1. This denominator on the left always less than the one on the right, so reciprocal will be greater than. So it passes the second condition. So that means that by the alternating series test, the sum is n goes from the original series 1 to infinity, negative 1 to the n plus 1th times 1 over n converges. See, but the absolute value diverged. So that leads us to our definitions for absolute and conditional convergence. If the sum of the absolute value converges, then the series converges absolutely. But if the sum of the absolute value diverged, like in this example, but by the alternating series test, so this would only be, the only way this can happen is if it converges by the alternating series test, then we say that the series converges conditionally. And get this also out of there. So we say that series converges conditionally. Okay, so we'll come back and we'll do a bunch of examples regarding topic 9, absolute conditional convergence. So we'll see you when you're ready.